So welcome to the final segment of the first module on disjoint set union. This is the third and the last video in like a three-part series, and I hope you have seen the first two videos because I don't expect this one to make a lot of sense without the context from there. So this is not a standalone video. We are going to actually implement the algorithms that we have already discussed for the two main DSU operations, which are FindSet and union set. So if you recall, we discussed a couple of different heuristics. So first we talked about union by depth, and then we talked about path compression and union by rank. So basically that's what we are going to implement, and the specific implementation here is in C++, but it's quite easily adaptable to Python or any other language of your choice. The implementation here is it's really elegant and simple, and it follows the pseudocode quite closely, so I think we'll have some fun. I should say that this implementation is heavily borrowed from the 4th edition of the competitive programming book. Now, even if you don't have access to the book, there is a GitHub repository that goes with the book, and that is freely accessible, so you can look that up. There's a link in the description. They have implemented a lot of other data structures as well, and this is a really useful reference to have, and you will find code in at least Python, C++, and Java as far as I remember, and maybe some other languages as well. So this is a really useful thing to bookmark and keep handy. Now for DSU in particular, if you want to test out the data structures that you implement, Codeforces has a really nice series of practice problems for DSU. In fact, you'll find quite a large collection of DSU based problems there. Unfortunately, we won't have enough time to actually go over all of them, but we are going to look at a couple of more examples from this section. So again, I'll point you to exactly where you can go. So this is not a standard contest. You'll have to have a Codeforces account, and then you can go to the EDU tab on the top of the navigation. So this is the education section, and there's one course there which covers many different topics, but you want to look out for the one on disjoint set union, which in turn has multiple chapters. Just go to the first one and go to the practice section. You will find a customized contest with a bunch of problems, and what we will be talking about here will be kind of geared towards solving the first two problems, which is essentially just asking you to implement DSU. That's the first problem. It's asking you to implement basically find and union, and also this extra operation which asks you if two elements belong to the same set or not. So we're going to look at how to take care of that. And in the second problem, it's very similar, except that you're also asked to be able to not just find the set that an element belongs to, but you're also asked to return the minimum and the maximum elements from that set. So that's the extra bookkeeping that we need to do. So we're going to discuss both of these problems in this video, but before that, let's actually implement the basic data structure. So we're going to do this in object-oriented style. You're free to just directly implement this using global arrays or whatever your preferred method is. But this way you essentially open up a convenient interface, and this becomes code that you can just set aside and invoke quite easily when you actually need it in specific contest problems. So this is the style that we are going to adopt. So the union find class is going to have a bunch of things. So it's going to have a vector array, which is essentially going to store the information about the parent pointers. It's also going to try and store the rank and the sizes of the individual sets. Now, the information in the rank and the set sizes array will evolve to being relevant only for the leader elements. We'll see how that works out. And we are also storing a little bit of auxiliary information in this integer num sets, which essentially keeps track of the number of sets that we are working with. So now let's look at the public methods. First, of course, we have the constructor, which is going to initialize your object with sensible values. So let's say that you initialize union find with n, which is to say that you want to keep track of n elements. And I'll come back to this, where, as I said, to not have to worry about indexing issues. If I want to do disjoint set union with a universe of size n, I will typically instantiate this with n+1, just so that I can freely talk about the element at the ith index actually being the element I. Okay, so we'll see that when we get to the main function. But suppose we're doing union find with n elements, then what we want to do is initialize a parent array of size n. In this case, this is a vector with n elements. And to begin with, remember that these are all singleton sets. So we want all the leader pointers to just be pointing to themselves. So p of I equals I for all I from 0 to n minus 1. Now, the rank tries to keep track of the heights of the trees. As we said, because we will be doing path compression, this is not really exactly the depth of the tree, but it's a useful upper bound to work with nevertheless. To begin with, all your trees is just basically one root element. So we're going to adopt the convention that these trees have depth 0 to begin with. All sets initially are singletons, so they all have size 1. So we are going to assign a value of 1 to every element in the set size vector. And finally, the number of sets that we are working with initially is in fact n, because remember that to begin with, every element is just a singleton set. So there are n of these sets. So we're going to initialize the numSets variable to n. So that's all of the initialization work. Remember that in a particular application, you might want to track more information. And if you do add more stuff here to your class, just make sure that it's properly initialized, because if not, you might run into all kinds of runtime errors and memory allocation issues. So this is simple, but it's really important. So just double check that everything that you're trying to keep track of is properly initialized. Now, with this out of the way, let's talk about the first operation that we want to implement, which is the FindSet operation. So the first thing that we want to check for FindSet, remember that we are doing path compression here, and this is a recursive implementation. So the first thing we want to check is if we are already working with a leader element. So that check is just to see if the pointer is pointing to itself. So if the element is pointing to itself, then we can just return that element. So that's the first if branch out here. But if you're not in this nice base case, then you need to actually walk up the tree. So one step at a time, let's go to the parent and try to invoke FindSet on the parent. And this is going to give you the value of the root of the tree. So remember, in path compression, we want to actually assign this root as the new parent of the element I. So that's what's happening here when we say p of I equals FindSet of p of I. So that's finding the root and reassigning the parent of I all at the same time. And this is also what we are going to return. So all of this is combined in this succinct one-liner. You could, of course, write this down a little more explicitly, but this works out just the same. So now, before we move on to working with the union implementation, let me write down a small helper function which will be useful both for union as well as for the specific problem that's there on Codeforces. So this is called the isSameSet function. So isSameSet will return true if I and j belong to the same set, and will return false otherwise. And notice that figuring out if I and j belong to the same set basically boils down to asking if I and j have the same leader element. So of course, it's possible that one of I or j themselves are leader elements. That's not particularly relevant. All we have to do is invoke FindSet on I and j and check if the outcomes of FindSet is identical on both I and j. If it is, then I and j do belong to the same set, and if it's not, then they belong to different sets. So hopefully this is clear. This follows just by the definition of the way representatives work and the promise that FindSet does its job properly. So that's isSameSet. Now let's go on to talking about union set. So in union set, well, when you want to take the union of the set that I belongs to with the set that j belongs to, the first sanity check is to see if these sets are the same or not. If the sets are the same, we don't have any work to do. So we just check if I and j are in the same set, and if so, then we just don't do anything, we return. Otherwise, remember that with union, we want to just make sure that the parent pointers are carefully adjusted based on the rank heuristic. So first, let's find the leader elements of the sets that I and j belong to. So let's call them x and y respectively, and let's make sure that x is always the element that has the smaller rank, that belongs to the set whose corresponding tree has smaller rank, where rank is going to be some sort of a proxy for the depth. So if the rank of x is larger than the rank of y, we make sure to swap the two, and after this we can peacefully make sure that x points to y, given that y is the root of the bigger tree in terms of the notion of rank. So we go ahead and adjust this parent pointer, and notice that the rank does need to be updated if you are combining two trees that have the same rank. Originally, when we were working with depth and we did not have path compression, this would have been a legitimate reason for increasing the depth. So if these two trees have exactly the same depth and one of them points to the root of the other, the final tree has a larger depth than before, and we're going to do just the same with the rank value. So if you're combining two trees that have the same rank, then you increment the rank of the tree that you just generated. And remember, this tree is being tracked by y, that's the current leader element, that's the current root, so you make sure to increment the rank of y. Now remember that we were also tracking the sizes of the individual sets and the total number of sets. Both of these values are affected by the union operation. So the size of the set that y is representing has now been enhanced, and it has a few extra elements. How many extra elements does it have? Well, that's as much as the size of the set that I belong to, which is in turn the set that used to be tracked by x. So we just go and look up the set size of x and update the set size of y. Now notice that the set size of x is now not giving you accurate information about the size of the set that x belongs to, because now x also belongs to this larger set. But this doesn't matter, because when you want to find out the size of a set that some element belongs to, you will not directly look up its set size, but you will look up the size of the set of its representative element. So that is why it's okay that some of the values in the set size array are not going to be completely accurate. What is crucial is that they are accurate for the leader elements. Whoever qualifies as a leader element in the current scenario, the set size information should be valid there, and that's why we have this update here. Now what about the number of sets? Well, you've just merged two distinct sets, so the number of sets goes down by 1. Notice that this does not happen if I and j belong to the same set, and this code will not execute because you have already returned the control flow back to the main function, if that were the case, on the third line in this code snippet that you see on your screen. So that's essentially union set. You want to just go back and check that everything that you were tracking has been appropriately updated as it needs to be. I believe we have more or less covered everything. So this is the implementation of union set, and let's just write a couple of small helper functions. As I was mentioning earlier, if you want to find the size of a particular set, you don't just return the value in the set size array, but you actually go to the set size array as indexed by the leader element of the set that I belongs to. So you do FindSet of I and you do the set size of that element, and that's what you return. And if you wanted to know how many sets there are right now, you can simply return num sets. So these are two useful helper functions to have. So now if you were solving the first problem in the Code Forces contest that I mentioned, which is also linked to in the description, then essentially what you're given is a sequence of queries which are either union queries or same set queries. So essentially you just have to perform a sequence of unions, and sometimes in between you get this question of, are these two elements in the same set or not? So essentially this is how you would implement it. Given that all the work has already been done for you, this implementation should be straightforward to understand. So in the first few lines, this is pretty typical. We are just taking in the input. Notice that I'm initializing union find with size n+1. This is once again so that I can conveniently think of the ith index is tracking the ith element. If you were to initialize this with n, then you would have to remember to adjust for the indexing a little bit, because even the notation in the input is that the elements are from 1 through n. Of course, if the elements were being denoted from 0 to n-1, then you wouldn't have to make this adjustment one way or the other. So that's again a small detail, but an important one, because it's the sort of thing that can be annoying to debug when it doesn't fall in place correctly. So I just wanted to flag that. But apart from that, everything else is pretty routine. You read off your queries, and depending on whether it's a union query or a same set query, you invoke the appropriate functions. Now from here, it looks like we never really use FindSet in spite of implementing it, but notice that both union set and same set actually make use of FindSet in their implementations. So really everything that we have written is more or less being used, except for some of the helper functions. Those aren't really coming into play in this particular example, but again, it's useful to have them because you might need them depending on the situation. So that brings us to the end of the first exercise, and the second one is actually very similar. It kind of builds on this and just asks for a little more information. So just like here, you have a bunch of union queries, but now you also have these get queries in which you are given one particular element, and your task is to return the size of the set that this element belongs to. We have already implemented this, by the way, with the set size helper function, but apart from the size of the set that this element belongs to, you're also asked to output the value of the largest and the smallest elements in the set that this element belongs to. So let's just briefly outline how you would handle something like this. I'm not doing this from scratch, but I'm just showing you the extra information that you would need to store to be able to output the values of the largest and the smallest elements in any set. So to begin with, let's add the MaxSet and the MinSet vectors to the class definition, and although I'm not showing it here, you should remember to initialize them properly. So to begin with, MaxSet and MinSet of I will both have the value I, because you're working with singleton sets, so the maximum and the minimum elements both equal to the only element that you have in that set. So do remember to do that in the initialization function, in the constructor, and also add these helper functions where you're returning the values of the maximum and the minimum elements by, well, not directly returning the value, just like we saw with the set size array. The values at I may have become meaningless over time, but you will be tracking them correctly for the leader elements. So to find out the maximum value in the set that contains the element I, first find the representative element of the set that contains I, and then look up MaxSet for that element. And this is analogous for MinSet. So we have these two very simple helper functions which will give us the values that we want, and you can invoke them when you are writing down your output in the main function. Again, I don't show the main function explicitly because this is a really straightforward addition, and in any case, if you want to see the entire code, of course you can always go to the official GitHub repository and look it up there. So the one thing that is very important to do is to update the values of MaxSet and MinSet for the leader elements when you actually implement the union. Notice that these values are not affected when you do things like FindSet, because nothing about the structure of the sets changes when you do FindSet. But when you do union, then the values of the max and the min can change. So when you're doing union, remember that we had X and Y as being the leaders of the sets represented by I and J. Once again, if X is equal to Y, you don't need to do anything because the set itself does not change. There's no union that's really happening, so we don't have to worry about that case. But in the other case, when you are actually merging two sets, remember we said that we will set P of X to Y, so the set that was being tracked by X is getting absorbed into the set that is being currently represented by Y. So we do do have to update the values of maxset y and minset y to account for this new information. So these newly added elements may actually upset the old max and min values. So that's essentially what these two lines of code is doing. It's very simple, but it's crucial to ensure that you maintain correctness as you go along. So essentially, look at the maximum element that was there in the set that was being tracked by X, and if that's larger than the maximum element in the old set that was being tracked by Y, then the max set of Y should be updated so that it reflects this new element as the maximum. However, if the maximum was smaller than the maximum element of the set being tracked by Y previously, then you don't need to change anything. So you could write this down as a if-else block, but it's equally accurate and perhaps visually simpler to just take a max of the two old maxes, and similarly for min set, you take a min of the older mins. So hopefully this update makes sense, and this ensures the accuracy of the max set and the min set arrays, at least on all the elements that are representatives at any stage of the algorithm. So that brings us to the end of this discussion on basic DSU implementation. Now that you have your own version of DSU, you are prepared to tackle problems that use this data structure. Of course, these two problems that we have discussed so far were very explicitly asking for a DSU implementation. Many problems have the DSU demand kind of hidden away in a more subtle way, and we will see a couple of examples of problems where DSU comes in handy, but it may not be completely obvious that that's what you need to invoke. So there will be links to a lot of practice problems that you can try out on the course website, but in the meantime, in the rest of this week, we will look at a couple of different problems quite explicitly. In the meantime, I hope that you have a chance to try out everything that we have discussed so far, and as usual, if you have alternate implementations in Python or Java or any language of your choice, please do make sure to submit a pull request on the official repository. I look forward to seeing your submissions, and we'll keep the conversation going on Discord. Thanks so much for watching so far, and I'll see you in the next video. Bye for now.